click the red subscribe button right under the video and also the bell icon to get notification on any of our latest updates on our videos.
Welcome to another Smart BU Guides tutorial video. This is working with Excel, and the questions are mostly related to chemical engineering, especially if you read the narration of the question. Now, the narration of the question says a 20-liter storage tank is filled with ammonia, and the storage has an over-design factor that's a pressure safety factor of 10% and the bursting pressure rating Pmax of 3,500 psi. Now, the RK equation of state can be used to evaluate the pressure as a function of temperature and molar volume, and the mathematical expression of the RK equation is shown by this equation here, where P is the pressure in Pascal, R is the universal gas constant in joule per mole per Kelvin, C is the temperature in Kelvin, V is the molar volume in meter cube per mole, A and B are the RK equation constants, which can be calculated using equations 2 and 3. That means A can be gotten using this and B can be gotten using this, where Tc is the critical temperature for ammonia gas, that's 405.5 Kelvin, and Pc is the critical pressure, which is 1636 psi. Now remember that our equation told us that our pressure is in pascals, so we are supposed to convert our values of pressure given in psi to pascals. Now, main question is prepare a spreadsheet using Microsoft Excel to solve the following cases. The first one says if the tank is charged with 5 kg ammonia, what will be the maximum safe operating temperature, C safe, for the storage tank? The second one says at 480 degrees Celsius, what is the maximum mass of ammonia that the storage tank can hold safely? And we're given a hint that we can pick an initial guess on mass of ammonia between 2 to 7 kilograms. And the third one wants us to evaluate the vapor pressure using Antoine equation at the temperature of 100 degrees Celsius, and we're given an equation log to base 10 of P is equal to A minus B over C plus T, where P is the saturated pressure in bar, and A, B, and C are the Antoine coefficients, which have numerical values for pure ammonia as A equals to this, B equal to this, and C equal to this. And we're given other bits of information. 1 bar is equal to 100,000 joules per meter cube, which is the same thing as Newton per meter square. 1 bar is equal to 14.5038 psi. 0 degrees Celsius is equal to 273.15 Kelvin, and molecular weight of ammonia, that's the molar mass of ammonia, is 17.03 gram per mole. Then we're given a relation between Pmax and Psafe, where Pmax is equal to 1.1 Psafe. Now we'll start by putting down our given values. Now remember that we were given Pmax in psi, so we'll have to convert it first using converting the psi to bar and then converting the bar to Newton per meter square. The same goes for our value of Pc. The value of Psafe is related to the value of Pmax, so we can put that down as a relation, show that the value of Psafe will be the value of Pmax divided by 1.1. Now Pmax is contained in cell E2, so we'll just put E2 divided by 1.1, enter, and to give us the value of Psafe. The value of R was given in the question as 8.3145 in joules per meter per mole per Kelvin, and the value of Tc in Kelvin was given as 405.5, and the value of Pc after the conversion gives us 11279,800, which is the same as 1.13 times 10 raised to the power of 7 Newton per meter square. Now the volume of the ammonia gas will be the same as the volume of the tank, because we were told that the storage tank has a capacity of 20 liters and it is filled with ammonia. So we'll convert that liters to meter cube, giving us 20 liters will be equal to 2 times 10 raised to the power of minus 2 meter cube. Our capital letter M in gram per mole is our molecular weight of ammonia, which is 17.03 equivalent to 1.7 times 10 raised to the power of 1. Now we can look for our value of A using given values. So to do this calculation, we'll just make reference to the cell addresses of our required values. The equation goes A is equal to 0.4278 multiplied by R squared multiplied by TC raised to the power of 2.5 divided by PC. Now in Excel terms, we'll first put an equal to sign, and then since we are multiplying and dividing, we can put the items in the numerator in a bracket and then divide it by the value in the denominator. So we have 0.4278 multiplied by our value of R raised to the power of 2 multiplied by our value of TC raised to the power of 2.5. You now close the bracket and divide by the value of PC. Excel follows BODMAS. This is supposed to be point. So you press equal to and it will give you your value of A. Your value of B will be equal to 0.0867 multiplied by R multiplied by TC divided by PC. So you come here and put your equal to sign and then put the things in the numerator and bracket. That's 0.0867 multiplied by R multiplied by TC. You close your bracket and divide by the value of PC. Press your enter. So now we have the value of A and B. Now remember in the first question labeled A, we're given a mass value of 5 kilogram ammonia, and we asked to find the maximum safe operating temperature, which is T. It implies that T safe is related to P safe. So instead of using the value of P safe in this calculation, while we are plugging in the values in this RQ equation, this value will be the value of P safe, so that the value of T, which we are looking for, will be the value of T safe. But then remember that our V is the molar volume, not the ordinary volume, and that can be gotten by dividing the actual volume by the number of moles of ammonia. And the number of moles of ammonia can be gotten by calculating reacting mass divided by molar mass, and we're given our molar mass as 17.03 gram per mole. So we can create a space for number of moles and then get our number of moles as equal to reacting mass, which is 5 kilogram, which is the same as 5,000 gram, divided by our molar mass, which is this. Press enter. Then our capital letter V, which is the molar volume, will be equal to our volume of ammonia divided by the number of moles, giving us this value. Now we are going to find our unknown value of T safe using solver. Now solver is an add-in in Excel that is gotten usually under data, that is found under data, and if it's not there, you can go to file, go to options, go to add-ins, and you add it. We are going to take an assumed value of T safe, which is our unknown, and then we'll use the formula for calculating TP, that's the RK equation, using that assumed value of t. So it will give us a different value from our value of p safe, which we are using to compare. So here we have a space for value of p safe based on assumed t safe. That is, when we plug in our formula here, it will give us a value of an assumed value of p safe based on this assumed value of t safe. And then we are going to calculate the error, which is the difference between the assumed value and the actual value of p safe. Now we'll now go to solve and try to minimize that error between the actual value of p safe and this calculated value by changing the value of assumed t safe. Now after automatically minimizing the error, we are left with an almost accurate value of t safe. So here we go. We can choose our assumed value of t safe to be maybe 200, and then we plug in our formula for p. Now you can see the formula is in two parts. So this part will be in a bracket divided by this part, which is also in a bracket. So we'll have a very big bracket covering this bracketed numerator divided by the bracketed denominator, and then minus another big bracket in which you have a divided by all these in bracket. So here we go. We'll have equal to, this is the first big bracket, and then this is the bracket for the numerators. We have r multiplied by t, which will be our assumed value of t safe, and then you close your bracket and divide by this v minus b. V is your capital letter V. V is your capital letter V minus your value of b. And then you close all these brackets. Then minus the second part of the equation with the first bracket, and then the value of a here divided by, you have another bracket for the denominator. The numerator doesn't really need a bracket because it's just one value. So your denominator has t raised to the power of 0.5, t raised to the power of 0.5 multiplied by v, that's this v, then multiplied by this other bracket in which there's v plus b. Then you close this first bracket for v plus b, close the bracket for the denominator, and then close the bracket for everything. Enter. So you now take your difference. Sorry, the value of t here is supposed to be the value here, which is this, and you have your assumed value of p safe as this. Then the error will be equal to, we're going to square this because we could get a negative answer. The square of the difference between the value of p safe here and p safe here. So we square it. Now we'll try to go to solver and we'll put our objective as this cell here and put it to minimum by changing this cell containing assumed value of p safe. Then so we keep our solver solution, and that gives us an approximate exact value of the safe temperature T safe, which is 439.51 in Kelvin. Now we go to the second part of the question, which says at 480 degrees Celsius, what will be the maximum mass of ammonia that the storage tank can hold safely? And we're given a hint to pick an initial guess on mass of ammonia between 2 to 7 kg. So this is like the previous question where we have an unknown and we are supposed to pick a guess. Now here we are guessing on the value of m. And we know that our value of v is actually dependent on our value of m. So we'll have a new value of n, compute a new value of n in moles, which is equal to the reactant mass divided by the molar mass. But we don't know the reactant mass, and we are going to assume it. So we're told to assume a value between 2 and 7, so we can take maybe 4 kilograms. That's 4,000 grams. And in that case, our number of moles will be equal to this reactant mass divided by our molar mass, which is up here, equal to, this is our new value of number of moles. Then we'll have our new value of V. So we should just consider this as V, the new value of molar volume, which is a function of the number of moles, which is the reactant mass divided by molar mass, and the volume of ammonia gas. Now remember that as the volume decreases, pressure increases. Now the new value of the volume will be equal to the volume we have here divided by, so we have this. Now our P max based on assumed M max, which automatically changed our value of V, make a new one. So we have a big bracket for the whole first part, and then another bracket for the numerator of the first part, which contains R multiplied by T. R multiplied by T. Now here we were given our temperature in Celsius, which when converted to Kelvin gives us this. So we are using it. RT divided by our value of V minus B. Our B didn't change, so close this bracket and close the first bracket. Then minus another bracket. Then we have A, which is this, divided by our value of T raised to the power of 0.5, then multiplied by our value of V, multiplied by a new bracket and then containing V plus B. So we close this bracket, close that bracket, and remember this denominator is supposed to be under a bracket, so we'll have to close the third bracket. Now remember that we are comparing this value with the value of P max because the value of M max is supposed to go with the value of P max, because as the value of M, as the reactant mass increases, it implies that the value of our V decreases, and there's an inverse relationship between our P and our V. So it implies that since we have M in the denominator, that's the small letter m in the denominator, while looking for our molar volume. Our P max is therefore directly proportional to the M max. So our maximum value of M should go with our maximum value of P. So our error will be equal to the difference, the square of the difference between this P max here and the one here. So you square them and you get your answer. Then we go to solver and put our objective as this cell. We'll minimize the error by changing the variable of the assumed M max. So we solve. Now, interestingly, solver encountered an error value. So actually, I did some. We were asked to choose a value between 2 and 7. Not every value will actually go with the solution. If you assume that M max will correspond to P max. Check the equation. You can see that our V's are at as V increases, the value of P decreases and vice versa. And remember that V is a function of small letter m and capital letter M, where small letter m is the reactant mass, which is the assumed mass. That's the M max we're looking for. And capital letter M is the given molecular weight. So you can try changing your value of assumed mass to maybe something like 3,500 if you go a bit lower. Now, you can see that because n is a function of this and v is a function of n, they all change as you change your m. So you try going to solve again and put your objective cell as the error cell and your variable cell as the value of m. That's this, and you solve. Interestingly, solver gets a value that's computed for you. So you can, to verify your answer, you can check another value of assumed mass, and if it gives you the same value, you'll know that you are actually on the right track. So if you change this to 2,500 and you enter, you still follow the same path. It still gives you the value of 1,409, which is the same as 1.4 kilograms. Now for the third part of the question, we asked to evaluate the vapor pressure using Antoine equation, and we're given the values of A, B, and C, and we asked to find P. Now remember, this equation is for log P, so even after finding the solution to all this, we are supposed to take the antilog of our answer to get our P, and this P will be in bar. So we come here and we impute our formula. Log P is equal to A, which is this, minus the other part of the equation, which is B, divided by C plus D in bracket. C plus C, 100 degrees Celsius converted to Kelvin gives us this. So we have C plus C. And this is supposed to be have A minus B divided by C plus D. This is supposed to be C. So we press enter. This gives us our log P. Now our P in bar will be the antilog of this value, which using your calculator gives us using your calculator, you get the antilog of this value of log p. In Excel, the antilog, since it's base 10, it will be 10 raised to the power of this equal to 10 raised to the power of this. That's your antilog. And that's your P in bar. To convert it to Pascal, you can first convert from bar to Newton per meter square or joules per meter cube using this relation 1 bar equal to 10 raised to the power of 5 Newton per meter squared. So if you want to convert this to Pascal, which is the same as Newton per meter square, you will simply have equal to this value multiplied by 10 raised to the power of 5. And then paste